Here's our team in our controls lab configuring the San Jacinto DCS. We began this effort in October of 2010, and we completed the startup and commissioning of the second 36 megawatt unit in February of this year. The title of this paper is Real-Time Specific Work DCS Calculations, but it also describes implementing real-time calculations for turbine efficiency, reservoir enthalpy, separator and turbine exhaust steam quality, and the sensitivity of power output versus the condenser backpressure. The point is to maximize the value of your DCS by doing these sorts of calculations, historize the results for use by engineering and management, and present useful information in real time to your operators in order to give them the tools to improve your plant's performance. You spent roughly $1 million for your DCS. Maximize its usefulness to you. I'll be running through some mass and energy balance equations around the separator and the turbine, so a quick review of the turbine expansion line may be helpful. On this entropy diagram, I've plotted the 100% quality saturated steam line plus two constant pressure lines. The 5.7 bar A line represents the separator pressure. The 0.078 bar A line represents the condenser pressure. The vertical line that runs from the intersection of the saturated steam pressure line and the separator pressure line down to the condenser back pressure represents the idealized 100% efficiency turbine expansion, while this line next to it represents a more realistic 86% efficiency turbine expansion. The enthalpy at the turbine inlet is shown here as H2G, while the enthalpy at the turbine exhaust is H4, and the idealized 100% efficiency turbine exhaust steam isentropic enthalpy is H4S. The turbine's power output is equal to the steam mass flow rate times the actual enthalpy drop. The turbine's efficiency is equal to the ratio of the actual to ideal enthalpy drops. In reality, there are a few differences from this idealized situation. There's actually a pressure drop between the separator and the turbine steam chest due to frictional losses in the piping and stop and governor valves. If you assume an adiabatic pressure drop, one with no work or heat transfer, then you move a bit horizontally from H2G into the superheat region. This reduces your potential enthalpy drop due to the upward slope of the enthalpy at the turbine's exhaust pressure. There are also pressure and velocity losses at the turbine exhaust. The turbine's exhaust steam has a large specific volume and is traveling at high velocity, resulting in frictional losses in the ducting between the last turbine stage and the condenser. Also, the velocity and energy exiting the last stage blades is lost. So the used energy endpoint at the outlet of the last stage blades is somewhat above this H4 point. Another difference is the fact that your actual turbine consists of a series of expansions across a number of stages. At each rotating stage discharge, the steam will gain a little entropy before expanding to the next rotating stage. So the path actually follows a zigzag pattern. Here's a picture of the basic model I used in developing this paper. Two-phase brine flows out of the reservoir and enters the separator. 0% quality saturated liquid exits the bottom of the separator and flows off to reinjection. 100% quality saturated steam exits the top of the separator and flows off to the turbine. State 3 represents the steam properties at the turbine steam chest, while State 4 represents the turbine exhaust steam properties. The specific work is equal to the turbine's power output divided by the reservoir mass flow rate. Some basic equations are as follows. Here's the formula for the energy balance around the separator. Solving for the reservoir enthalpy gives this equation. Throwing in the mass balance, where the flow into the separator must equal the sum of the two flows exiting the separator, gives this equation. The DCS can use its steam tables to give the corresponding reservoir temperature and log this data in its historian for long-term trending. Starting off with the same energy balance, you can solve for the mass flash fraction. Throwing in the mass balance gives this. Rearranging, Substituting in for the enthalpy of vaporization, dividing through by the mass flow entering the separator, and solving for the ratio of the steam flow out of the separator versus the brine entering the separator gives this. On the San Jacinto project, we were getting a very respectable 31% or so mass flash fraction. Again, this may be a worthwhile parameter to have the DCS calculate and trend over the life of the plant. The turbine exhaust entropy for an isentropic expansion is equal to that at the steam chest. Using the lever rule, the isentropic entropy can be expressed using the 0 and 100% quality liquid and steam entropies at the measured condenser pressure. Rearranging and using the definition for the entropy of vaporization and solving for the turbine exhaust steam quality in terms of these entropy values gives this useful equation. You can also solve for the using the enthalpies and get to the same mass flash fraction. Rearranging, you can solve for the enthalpy, isentropic enthalpy at the turbine exhaust. This useful equation, along with the turbine efficiency, allows you to calculate the specific work. The turbine's power output can be calculated thermodynamically. The power is equal to the steam mass flow through the turbine times its enthalpy drop. This can be expressed using the isentropic turbine exhaust enthalpy, that important parameter defined in the previous slide, using the turbine efficiency. You can also get at the turbine power output from the electrical side of things. Solving for the turbine efficiency gives this equation. You can use functions in the DCS where you only calculate this value when the unit is close to full load normal conditions, and then use a first order lag function with an extremely long time constant, so that this calculated value only changes very gradually over a time frame of weeks. Basically, you put a big filter on the calculated value so that it doesn't move around too much, and then trend and archive this number over the life of the plant. And again, remember that simple but important equation for the isentropic turbine exhaust enthalpy. Using this equation and the calculated and filtered turbine efficiency, we can calculate the specific work. In reality, there are relatively fixed frictional losses that need to be accounted for. These might be on the order of about 300 kilowatts for a typical flash turbine generator unit. On the electrical side of things, solving for the turbine power output gives this. On the thermodynamic side, the turbine power is this. The exhaust losses are provided by your turbine manufacturer in the form of a graph of the losses versus the turbine exhaust velocity, or turbine flow, volumetric flow. These losses account for the exhaust duct frictional losses and the unused velocity energy at the turbine's discharge. Here's what a manufacturer's typical exhaust loss curve might look like. Equating the electrical and thermodynamic calculations for the turbine power output gives this. Equating the two and solving for the real enthalpy drop through the turbine gives this. The real turbine efficiency is just the real enthalpy drop divided by the isentropic drop. Solving for the actual exhaust enthalpy gives this. Throwing in the condenser liquid enthalpy and the enthalpy of vaporization gives the actual turbine exhaust steam quality, which may be of interest to trend over time. Again, the turbine power output is just the mass flow times the isentropic enthalpy drop times the turbine efficiency. Expressed on a per reservoir mass flow basis gives the specific work. Replacing the ratio of the steam to reservoir mass flows with the ratio of enthalpies equation from an earlier slide, and replacing the turbine exhaust steam enthalpy with that equation from an earlier slide gives this. Note that all these properties can be determined. The turbine efficiency can be calculated as shown in the previous slide and only allowed to change very slowly by using a long lag filter. but even if you just use an assumed fixed value, you can see that it won't have any effect on the pressure where the maximum value occurs. It will only shift the curve up or down. Again, you can replace the ratio of the enthalpies and entropies with their equivalent mass fraction expressions. This simple formula allows for an intuitive understanding of the specific work equation. The term in parentheses is simply the turbine's isentropic enthalpy drop. Of course, you must account for the exhaust losses in order to determine the real specific work. When you plot the ideal specific work over the range of commercially viable flash plant reservoir temperatures versus flash pressures, you get this graph. The shape of the specific work versus separator pressure curve is the same for all reservoir temperatures. Specific work rises quickly with increasing pressure, reaches a maximum value, and then drops off slowly with increasing pressures. This rising and then falling off represents the trade-off between an increase in the flash percentage at lower pressures versus higher steam enthalpies at higher flash pressures. But this doesn't take into account that at higher pressures, you'll get less flow out of your production wells. In any event, you most likely want to operate at close to the peak specific work point for your specific reservoir temperature, as shown in this graph. You can get extremely close to this optimal pressure value by choosing a flash pressure that has a saturation temperature that's halfway between the reservoir and condenser temperatures. But that midpoint calculation won't give you the actual specific work, as shown on this graph. In reality, there are pressure losses between the separator and the turbine steam chest. This graph shows a family of specific work curves for various pressure drops given a reservoir temperature of 250 degrees C and a condenser back pressure of 0.7 bar A. With increasing pressure losses, you'll get these lower curves. The optimal flash pressure where the curve's peak occurs increases. I've drawn a polynomial line through these peaks for this specific case just to show that the locus of these peaks follows a well-behaved curve. For any given set of reservoir temperature, condenser back pressure, and pressure loss between the separator and the steam chest, there's a specific work curve with a maximum value that can be calculated. Differentiating the specific work equation with respect to the condenser back pressure lets you put a hard number on the money you're losing if you don't operate at the lowest back pressure possible. I've found that this is something that operators often don't fully understand. Providing this as a real-time calculation and screen graphic, you can give them the tools to understand this issue so that they can help to maximize your plant revenues. But note that I haven't included the exhaust pressure loss curve in this equation, and so that would have to be taken into account, especially if you're able to operate at very low condenser back pressures. If you have any questions on this presentation, please feel free to contact me at tmcauliffe@powereng.com. tmcauliffe@powerengineers.com.